All right, so all that shit with limits that you've hated for the last 3 weeks, it's slowly getting tapered out. It's still going to show up on occasion, but we're going to use it to define how we're actually going to do derivatives now. And we're going to do some proofs with it to show that we can do the shortcuts. And then after that, we're going to do the shortcuts. So how to differentiate. Differentiation is another word for taking the derivative. So differentiate and derivative are kind of similar. So if we have a constant value for f of x, where like f of x equals like 5, then the derivative of f is the derivative of the constant, which is 0. We've got a bunch of notations for derivative. We've got f prime of x, we've got d dx, we've got y prime. I've seen dx. What else do we got? dy dx. There's a whole bunch of ways of marking notation. So this means the d dx, d over dx is, I guess I'll say it down here. Take the derivative with respect to x. If we add in the y, dy dx, it's the same thing. This comes down, we just add the words of y, and then with respect to x again. Take the derivative of y with respect to x. So the derivative of a constant equals 0. We'll show this using the limit laws in a second. If n is a real number, if we have x raised to the nth power and we take the derivative, we end up with n as the coefficient and the power is reduced by 1. The way I tend to remember this one, we have x to the n. When we take the derivative, the n comes down, we put it out front, and we subtract 1. And then if we have a constant times a function and we take the derivative, we can just factor out the constant. We'll show that in a second. I wanted to start off showing the power rule, though, this middle one. This top one is just a case of x to the 0. So the constant value one, this is like cx to the 0. So this is like a subset of that one. Subset. Let me give you time to write that stuff down before we start digging in. There's 30, 45 seconds. All right. So let's show the power rule works. What we want to do, recall what limit is. Its limit as h goes to 0 of f of x plus h minus f of x over h. Here, f of x equals x to the n. So we have x plus h to the n minus x to the n over h. This has an underline underneath it. If you actually look at the document in Canvas, it's a hyperlink. I'm going to go show you Pascal's triangle in case you've never seen it. It's a miraculous thing for multiplying out binomials quickly, like super quickly, and it's so easy to do. And x plus h to the n power is a binomial. So like, I don't know how to multiply that out without using Pascal's triangle because we don't know what n is. If we knew what n is, we could actually just multiply them all out. It would take a really long time to do, but we could do it. Let me show you Pascal's triangle though. So here's that document. When you click on the hyperlink, it takes you to here. And that's a little hard to see. There's a video go with it. I opened up the image a little bit bigger. What we do is we make this pyramid and there's ones along the diagonals. Then as you go down, if there's two numbers, the number below it is the sum of the two numbers above it. So this 2 equals 1 plus 1. This 3 equals 1 plus 2, as does this 3. This 4 right here is 1 plus 3. 6 is 3 plus 3. 4 is 3 plus 1. Jumping down to this row, 6 is 1 plus 5. 15 is 5 plus 10. 20 is 10 plus 10. These correlate to the following binomial products. The way you do it is you start with the first one, a, and you have it to the maximum power, n. You got 1 a to the n. These end up being the coefficients for it. So like if we're doing a plus b to the 6th power, we have 1 a to the 6th power. Then the next one is 6 plus 6. We bring a down by 1 and raise b up by 1. And then the 15 comes down, we raise or lower a again. So notice a keeps going down, a to the 6th power, a to the 5th power, a to the 4th power, a to the 3rd power, a squared, a, and then a is gone. And b is going up. This is like b to the 0 power, b to the 1st power, b to the 2nd power, b to the 3rd power, b to the 4th power, b to the 5th power, b to the 6th power. So you just, the first one, you lower the exponents down one at a time. And the second term, the b, whatever it is, it doesn't have to be, it can be something like negative 5y. It goes up by a power each time. And then the coefficients in front of it are these. Sometimes it's going to take a little more work. Like if you've got negative 5y and you're cubing it, you have to cube it, then multiply it by the coefficient. So it can get a little bit messy. Check it. If you've never seen this before, check it out later on today. Like play with it some. I'm going to show you what we're doing with it here. So we still have limit as h goes to 0. And now I'm going to do x plus h to the nth power. This is I'm gonna put that 1 over h out front real quick. So the first one is x to the first thing to the maximum power with the coefficient of 1, and the h to the 0 power, which is just 1. And then I guess the other thing I wanted to point out, I gotta go back to it real quick. These numbers, the first or the second number in each row is the exponent. You guys see that? So basically this diagonal right here, going right here, this diagonal is the exponents. So this bottom one is a plus b to the 6th power. It's got a 6 in the second spot. That's what we're doing right here. We don't have a 6, we have n. This is going to be n, x to the n minus 1. H goes up 1. Then I don't know what this term is. I'm going to call it a2. X to the n minus 2, h squared. So we follow the pattern for a little bit. I do know when we get down to the n again, it's n down here, x, h to the n minus 1, and then finally h to the n. That is the binomial expansion of x plus h to the nth power. Then we have minus x to the n from that. The a sub 2 is just a coefficient. I don't know what it is. What cancels out here? Let's take a look. That looks like a bad pen. See if this one's got a finer point. Not really, but it's at least darker. I still got the 1 over h. The 1 over x to the n right here, that cancels out with that right there. Those two cancel out. And I have n x to the n minus 1 h plus a sub 2 x to the n minus 2 h squared plus n x h to the n minus 1 plus h to the n. Each of these has an h in it. So we can multiply the 1 over h in. And we'll get limit as h goes to 0 of n x to the n minus 1 plus a2 x to the n minus 2. H squared goes down to h. I didn't put my dots in there. I should have. And now when we take the limit as h goes to 0, this goes to 0, this goes to 0, this goes to 0. The only thing that doesn't go to 0 is that. So the derivative of x to the n, which is the limit as h goes to 0, x plus h to the n minus x to the n over h, all boils down to n x to the n minus 1. Yeah.
So is this a proof for derivatives?
It's a proof of how it works. We're not gonna do this. We're just gonna take the cheat shortcut from now on.
Okay, thank God.
Right?
This expansion stuff is kind of going over my head.
Okay.
Like, I don't see where the expansion started and where it ended.
So the expansion is just the stuff in blue right here. It comes from. Let me try to line it up a little bit better down here. So we had like if it's a plus b to the n power. For any given, for like if it's a plus b cubed. The row when you do the pyramid is 1, 3, 3, 1. So what I'm going to do is I'm going to write a cubed b to the 0, a squared b to the first, a to the first b squared, and a to the 0 b to the third. And then I'm just going to put these coefficients in 1, 3, 3, and 1 and add them together. Now we don't have a and b, we have x and h. So like x plus h cubed is 1x cubed h to the 0 plus 3x squared h to the first plus 3x h squared plus x to the 0 h cubed. That would be x plus h cubed. Now the h to the 0 is 1, that goes away, and the x to the 0 is 1 also. Then we would have had, if we were doing x cubed was our proof, then we would have had minus x cubed. Nope. Notice the x cubes go away. And we would have had 3x squared h to the first power plus 3x h squared plus h cubed. We still would have had a 1 over h out front, and we still, I hadn't been writing it down, we would have had that. Maybe I should have started with something like a cube and then done the n, the general term with the n. Is this a little better?
Yeah, I get it now.
So it's following this pattern. The h goes in. We got the limit as h goes to 0. But now this is just 3x squared plus 3xh plus h squared. And as h goes, oops, 3xh like that. And as h goes to 0, this is just 3x squared. This would have been starting with the derivative of x cubed. Because that was my function there. F of x is x cubed. So notice if it's x cubed, the idea is we bring the power down and then we subtract 1. 3 goes down in front, and then 3 minus 1 is 2. Does that help clarify for other people as well? I'm sure Matthew didn't have the only question there. I think that's a better approach. Sorry, my first time teaching it. I really like the binomial expansion, the Pascal's triangle. It's a really fucking neat triangle. Like you can do x or a plus b to the fucking 20th power really quickly without multiplying that shit out. It's really handy. Although you do kind of got to make the pyramid. Because you don't know what the coefficients are and they're not like intuitive. Like 6, 15, and 20. They do, the pattern goes up and then it hits a middle point for the coefficients and they start going down again. And they repeat. So they like follow a pattern. If there is an odd number in the row, like 1, 6, 5, 15, 20 is 4, 5, 6, 7. There's 7 terms here. Then they go up and then they go back down. If there's an even number of terms, the middle 2 match, like the 10s match, the 3s match, the 1s match. But like having a simple pattern for what the 7th, 8th, 9th, 10th is, you literally have to kind of like write out the triangle. Thankfully, it's just addition. So the triangle, you start off with ones like that. That's how the triangle starts. This is Pascal's triangle. And you bring one, the entire size of the pyramids all have ones. Pyramids, triangle. It's called a triangle. Pascal's pyramid would have been better than if we had the piece. And the way you're getting the numbers in between is you're adding these. This is 1 plus 1. I put a 2 there. Here I do 1 plus 2, and I get a 3. 2 plus 1 right here. I get a 3 there. One plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So the triangle is made with just basic addition. Kind of neat. I think this was named after, I think the name is Blaze. Spelled like that, Pascal? I think. I don't even know if it's pronounced Blaze. It's a French name. All right, so basically what we've shown right now so far is if we're taking the derivative with x to the nth power, we don't have to use limits anymore. We can just bring the power down and lower the power down by 1. Power down as a coefficient or as a multiplier. And then lower the power by 1. That's really handy. That covers everything. This is just like a one-term thing. The next thing we're going to do is we can show that it doesn't need to just be x cubed. We can have a multiplier in front of it, like a constant like c. So it could be like 5x cubed, 10x to the 5th. The next proof we're going to show is that that just multiplies the end result. A Jim Bro name? What does Jim Bro mean? Obtool. What's GYMBRO? Is that like slang for anything? Or is Ainsley just making shit up? No one here. I don't see. Okay, I feel better. I didn't know it. That's what she put. Jim Bro name.
It's kind of like it's like
Okay, for today. Okay. Go ahead.
it's like a meathead.
That's what it sounded like. Like someone that's at the gym. Not all people that go to the gym are meatheads, though. I know some pretty fucking smart people that are strong. Pisses me off. You're not supposed to have brains and bronze. It's not fair. I guess I could too if I just wasn't a lazy fuck. I could go. I could go work out. All right. All right, let's prove this top line. So this is like saying ddx of 5x squared is the same thing as 5 times ddx of x squared. Just to put this in a little bit of like non-big shit. We already showed what this would have been. We bring the power down, we lower it by 1. And then we still have a 5 on it. So this would have been 10x. The derivative of 5x squared is 10x. All right, so ddx means doing that limit thing. Limit as h goes to 0. To do this, I'm going to say like g of x equals c f of x. Because I think this will make it a little bit clearer. So I'm going to do ddx of g of x. So I would have g of x plus h minus g of x over h. And if I substitute in the f or the f's, I'm going to do this as 1 over h. I've got c f of x plus h minus c f of x. All right, so I'm going to multiply the 1 over h in. I'm going to factor the c out. I haven't done anything with the limit yet. I'm just doing some basic manipulation of these things. The next step will take advantage of limit loss. This equals the limit as h goes to 0 times c. And then all of that is times the limit as h goes to 0 of f of x, plus h minus f of x all over h. Sorry, the page got rotated. This is just c. There's no h in it, so this is just c. And that's the definition of f prime of x. Or d dx of f of x. Those of you that were in here like early, I had said my brother has had hair down to his ass crack for like over 30 years. He's had long hair and he got it cut this weekend to like the nape of his neck. He's got a man bun. And he said he was doing it because he's a plumber, he's getting a receding hairline, and it just like the long hair in the back and like no hair, like the receding hairline wasn't a good combo. So he got the man bun. So I took a picture of myself and I said, no way, receding hairline here. Ha, ha, ha. We're like less than a year apart, so like we're very competitive. We are exact opposites. Like I'm brain, lack of brawn. He's brawny, lack of brain. He's a gym bro. His response was, "I'm still more handsome even with the receding hairline." Good times. We didn't get along for over 20 years. We had to become adults before we got along. We did not get along as kids. He was so easy to taunt because he's a meathead. I would use like words, I would pay him a compliment, but it would be a word that has a lot of syllables, like courageous or shit like that. Something that I knew the more syllables it had, the less likely he would know what it meant. Like courageous, he knows, but like I can't think of an example right now. But I would use like words that paid him a compliment. But since he didn't know what it was, he thought I was insulting him, and he would get pissed off. Oh my god, it's great. All right, so we can combine, like we did here, we can combine this constant coming out with their polynomial thing to now do anything like this. So if we want to take the derivative of 5x cubed, f prime of x means do this, which means bring the power down as a multiplier and lower the power by 1. So this would be 15x squared. Yeah.
So would f prime also be the tangent line to x?
F prime of x is the slope of the tangent line. To f of x at x. I guess that probably reads a little bit better if I throw in a 0, like x sub 0. You could have the generic form as well. Like you can have the generic form of the slope, but anytime you're actually going to use it for the slope, you would do it at a specific value. So you guys do a couple. You think I would have organized that on the screen a little bit better, but I did not. So those are 4 different things. Try doing the power rule on these real quick, and then we'll do them together. Give you one more minute, then we're gonna continue. We have an example in a little bit, Matt, with slope of the tangent line. You're not even paying attention to me. Like, fuck off, Jones. I don't respond to Matt.
So Matt? Sorry. Okay, I usually go by Matt.
Sorry,
What'd you say?
I know you told me. I said we're gonna, in a little bit, we're gonna have an example with slope of the tangent line.
Oh, we are?
Yeah,
Okay.
like that's one of the prime uses of this, so.
Yeah.
It'd be silly to not do it.
I was doing the homework for like 1.8 and 0.1, and I couldn't figure out the formula. And I searched up like how to do this stuff, and they just used the derivative.
Yeah, most times, right? Calculus is a long, there's 3 fucking semesters. After today, well. After this week and maybe the next week, very rarely will you use limit laws. Ever again, you're gonna jump to derivatives every single time. The limit laws are the basis for how derivatives work, though. So like, there are people that are like, I just want to do this, I don't want to learn about the limit laws. But then there's everybody else that's like, why the fuck is that? Who gives, what's the connection with this? What does this even mean? Like just saying it's the slope of the tangent line, why? Why is it the slope of the tangent line? And so like we can show with limit laws how it works. And it's based on rate of change. All right, so on the 10x to the 9, I can bring the 9 down and lower the power to 8. So this would be 90x to the 8th power. On this one, I can bring the 8 down. And I would have 7, and the exponent drops down to a 7. So this would be 56x to the 7. Here we bring the -4 down. You might be inclined to say one lower of -4 is -3, but that's not the case. -5 is the lower number. So this would be -12x to the -5. And here we bring the -7 down. And we get 14x to the -8. As a reminder, the negative exponents just means move it to the bottom and make the exponent positive. In fact, in 2.4, we're going to do something called the product and quotient rules. Quotient has a rule for doing these derivatives when something's on the bottom. When we get to 2.6, we'll show how to rewrite the quotient rule as a product rule just by doing negative exponents.
Professor?
Yeah.
Why does the 7x to the 8 stay out there? That's a 7.
The 8 drops to a 7.
No, why is it's 7x to the 8th power, right? That's how it starts. Why does it stay at 7?
It doesn't.
It's off screen. Oh, it's off screen.
Oh,
I'm crazy with that. Thank you.
sorry.
It's okay.
Like, what are you tripping on?
Yeah.
Like, doesn't say that. All right. That's just a single term. How often are we doing the derivative of just a single term? How often is our function just a single term? Not very often. It's usually a polynomial. So can we expand this concept to polynomials where we have a bunch of terms? One second, it's my dentist. Hello? Yeah. I will see you or her. Okay, bye. Dentist appointment tomorrow. They just wanted to confirm. They're gonna be happy to find out that like one of my back wisdom tooth on top, like literally just fucking fractured. My back wisdom tooth, if you like looked at it from the top, they're not circular, but you know, whatever the shape of a fucking tooth is, like 3 weeks ago, like just a piece just broke off. I never felt it. I never had something hard like that, like a piece of tooth. Like I must have swallowed it immediately and not known it was there. But it's got like a rough, jagged edge right there. And it's the first time I've ever had that with any tooth. I've had so few cavities. I've had like 3 cavities in all my life. They're gonna have fun with this shit. Now they've been pushing me to get my wisdom teeth pulled for a while. I'm like, they don't hurt. I know getting my wisdom teeth pulled hurt. Why the fuck would I want to do that? And now they're gonna be like, guess what we're doing? We're pulling that motherfucker. I know that's what they're gonna say. They're gonna say, no cap, we're pulling it. All right, so everyone ready for? Yeah. Oh.
You put 14 by the 8. Why don't you do that? And maybe it's 12x.
Put that 5x to the 5th down on bottom?
Yeah.
I can't. I just did it. That works just fine.
Oh.
So this becomes negative 12 over x to the 5th.
Oh.
I just hadn't done it. It was more of a reminder thing. All right, you guys ready for some more? We did single terms or monomials. Let's take a look at polynomials. But because Matthew loves it so much, what are we gonna do first, Matthew?
3x squared plus 1.
No, we're gonna prove it with limit loss. It's quick. It's actually quick and painless on this one. But the point is, if you take the derivative of a couple things added together, like say 3x squared plus 1, 3x squared would be f of x, and g of x is 1. That we can just do the derivative piecewise, one piece at a time. So the derivative of a sum of a few functions equals the sum of the derivatives. Derivative of sums equals sum of derivatives. And same thing with subtraction, because subtraction is just addition of the opposite. And because Matthew loves it so much, this is all for you.
Very considerate.
You're welcome. I'm glad thank you for appreciating it. It's good of you. This becomes, everywhere we see an x, we're going to do x plus h. Minus I might need to slow down a little bit. I'll pause there and wait for you guys to finish writing it. As a reminder, on Saturdays, I'm in the Mesa Center over on Whiteside campus. Cynthia keeps coming. She's tearing it up.
Is it always at the same time? So it can go.
Yeah, it's always at 9 to 12. I'm also on Zoom from 9 to 11 on Fridays. All right, so we could take this minus sign and deliver it to each one of these. So I can break this up into limit as h goes to 0. I'm going to put all the f's together. And all the g's together. And now we can split it up. Because fractions can be separated. And then when we have different things like that, the limit laws allow us to separate those out. Finally, that first one is f prime of x. And the second one is g prime of x. Or d dx f of x plus d dx g of x. Which can also be written as df dx plus dg dx. They're all the same meaning. Because having one way of writing it wouldn't be enough. We gotta have a shitload. You won't see me, I said capital D is one of them. You won't see me use that. That's like some like end game shit. I didn't see it till I was doing like graduate school mathematics, that big D. But all of these are common notations. And the reason why is these two different things were developed at the exact same time in different parts of the world. One by Newton and one by Leibniz. Leibniz. I don't know how to fucking say his name. What does that mean for us? It means if we want to do dy dx, we can actually separate it up into each of these. And this is a line, like a skippable line. As long as you don't fuck up the next line. we bring the power down and lower it by 1. This is a skippable line too. And the derivative of a constant is 0. And we end up with 6x minus 4. Ready to see it? Let's look at the. We're going to have an example for you, but we're going to merge it in with doing the slope of a tangent line. So you get some practice in a second. Sunzi's still right, so I'm going to wait a second. I'd rather. Yeah, but if you're not paying attention, if you're writing that one while I go to the next one, you're still behind. Might as well wait a second, make sure everyone else is done writing too. Like you're the only one I can see with the pen, but that doesn't mean others aren't. People online might still be writing too, they just don't speak up. Only a certain someone does, and they've begged me to not say their name again today. Because maybe. That wasn't me that had your name in my mouth. That was somebody else. You probably didn't hear him. Oh, she heard you.
No way.
Yeah. That's surprising because maybe there's a speaker closer to you than like you're further from me than the speaker is or something. Because like for me, that was quiet. You said it pretty quiet. That was Matthew, just so you know.
You didn't have to know that.
She didn't. Guess what? She does now, though. All right, onward. At what point does the graph of y equals x cubed minus 3x plus 4 have a horizontal tangent line? What does a horizontal line have? What's special about a horizontal line?
Slope of 0.
It's a slope of 0. That's correct. So we're really looking for slope of 0. And we want to find out what x values at what points. These are like what x, y values work for this. Slope of 0 would be where f prime of x equals 0. Or y prime equals 0. So what is go ahead and take a second and take the derivative of that and set it equal to 0 and try to figure this out. Oh, there's some algebra in this shit. The fuck, Jones? That was 2 semesters ago. Why do I gotta do algebra? So if I take the derivative, I bring the power down, lower it by a power. And when it's just x, it falls off. That's the derivative. We set it equal to 0. We can divide by 3 and we get down to x squared minus 1 equals 0. Just as a refresher for your mathematics, like algebra, which may have been a while, there are a couple ways to proceed. One of the ways, option A, is to factor that. That is x minus 1 times x plus 1 equals 0. And we can set each one of those equal to 0 since their product is 0. And we get x equals 1 or x equals -1. Shorthand notation is plus or minus 1. That's option A. Option B, another way to do it is to add 1 to both sides. We get x squared equals 1. And then take the square root of both sides. And when you take the square root of a number, it's plus or minus. That gives us the x values at those points. Now we can just find the y values by plugging them in. When x equals 1, y equals 1 cubed minus 3 times 1 plus 4 is 2. So I have the point 1, 2. And when I plug in -1, I get -1 cubed minus 3 times -1 plus 4. This is -1 plus 3 plus 4 is 6. So -1 comma 6. Those are the 2 points where the slope is 0. We will see in later sections what's going on with that. This is this 2, 4, 6, 1, -1. I'm going to put those points in green because that's how we calculate them. 1, 2, and -1, 6. So a horizontal tangent line means like that. And we are going to see that the graph does something like this. So the horizontal tangent lines are where there's peaks and valleys in the graph. That's chapter 3, I think. But that's where we're going with it. It actually crosses exactly 4. So higher derivatives, this paragraph has a long way of saying, so long as the derivative exists, we can keep taking derivatives. So we would start with f of x. The first derivative is known as f prime of x. Then we have f double prime of x, f triple prime of x. When we get to 4, they put it in parentheses like this. And the only requirement is the derivative keeps existing. These are the only real notations you're going to see in this class. So find the first four derivatives of y equals x cubed plus 5x squared minus 2x. Go ahead and take the derivative, then take the derivative again, then take the derivative again. Do it 4 times. This will give you a lot of practice in quick order taking derivatives. Yes. A student asked if the derivative still exists if it is 0. Yes. 0 is a constant, so you can take the derivative of it. It's just still 0. That's a great question, student. He who will not be named. Lady Voldemort? Voldemorta? Voldemorta. I have a friend, his name is Javin, Javin. Voice to text will not fucking recognize it ever. So I just started calling him Voldemort when we were in and doing chat over Messenger. There's a bunch of us that are in their group. I would just call him Voldemort because it picked up fucking Voldemort just fine. Would not pick up Javin, no matter how I did it. All right, so y is that. So y prime would be 3x squared plus 10x minus 2. Y double prime should be 6x plus 10. Y triple prime is just 6. And d to the 4th y dx to the 4th is 0. It looks kind of weird writing y to the 4th like that. It looks weird. That's it for 2.3. 2.4. We got plenty of time to get a lot done. I don't know that we'll finish, but this was anticipated. Still writing it down. Did you guys get that? Okay. And so the 5th derivative is 0 also. And the 6th derivative is 0 also. All right. So before Matthew gives me a shit bit, this is what the product rule and quotient rule are. I am not going to go through the proof, but the proof uses the limit laws. But you can go ahead and write them down for your purposes. We can also take like a 5-minute break 10-minute break. If anyone needs to use the restroom. Let me put pause on the recording. Okay, so those of you that are writing it down, in the red spot, I showed the difference between those two lines. We added and subtracted f of x plus h times g of x. Because that's like saying, like, if we add 5 and subtract 5, we've effectively added 0 and we haven't changed the problem. That's the idea. Then these two are broken up and put over here. And these two are split off and put in the front. I changed the order of them. Different than the book does. The book likes to do, and almost every other, like every book on the planet, writes this as fg prime plus f prime g. Because if I left them in the same order, these would be switched. The reason why I like it in this order is because the product rule doesn't just have to be two products. Check this out. If we had ddx of f times g times h times j, like 4 different things multiplied together, you just have to go through them one at a time, and you will have addition between each of them. And if you go from left to right, it's easy to remember how to hit them all. It's a simple pattern. The derivative or the product of the derivatives works like that. Or derivative of a product. So notice all I did is I had the derivative on the first one there, the second one here, the third one here, the fourth one here, and they're all pluses. Now, you're probably not going to do, well, I know you're not going to do 3 of them in this class unless you decided to break up like x cubed into x squared times x. If you were like crackhead or something. The generic thing is not as helpful as just doing, though. So I'll give you a couple more minutes to write down for those that are writing down, and then we're gonna do. We got a classroom of doers in here. Back to make sure I've got enough space to write everything down. I'm gonna start writing the next problem, or the problem we're gonna do on the next page. Alright, let's take a look at it. What we're gonna do when we do dy dx is we're just going to apply the derivative one at a time. We can do ddx of the first group and leave the second group alone. And then we do leave the first group alone. And then we do ddx of the second group. Maybe I shouldn't say ddx, it's derivative with respect to x. That's my lazy way of saying it. I'm just reading it as is kind of thing, but it's all, this is derivative with respect to x. So this one isn't going to change. And this one doesn't change. But if I take the derivative of the first parentheses, 2x squared goes down to 4x to the first power plus 0. And this one goes down to 3x squared minus 7. So we have 4x times x cubed minus 7x plus 2x squared plus 5 times 3x squared minus 7. I think if you left it there, it'd be fine. I'm not, just to work with this a little bit more. If we distribute the 4x, we have 4x to the fourth power minus 28x squared. And then I got that plus sign between them. And I'm going to multiply this stuff out too. I've got 6x to the fourth power minus 14x squared plus 15x squared minus 35. So dy dx is going to end up as 10x to the fourth. This 15 minus 14 is 1, and then we add negative 28, negative 27x squared minus 35. It's crazy that we don't have any cubes or anything to the first power here. Yes, Matt.
Can I ask why we couldn't just take the derivatives of each term individually and added them together? Like, why didn't we take the derivative of 2x squared plus 5 and then the same with like a x cubed minus 7x?
And just add them together
Is
separately?
that wrong?
Yes, it would be wrong. So like if we did that. So question. Can we do 2x squared plus 5 derivative plus x cubed minus 7x derivative? Is that like what you're saying?
Yeah.
So if we did that, we would have 4x here plus 3x squared minus 7. And notice these two are not equal. So
But that'd be just normal like that, so adding problem, like adding two different.
these are multiplied together, so like this is a coefficient, the x cubed minus 7x is like a coefficient on that. And if we had the coefficient, like we had 5 times x to the fourth, we didn't just ignore the 5. So like, but now it's not just a 5, it's a, does that
Yeah.
clear it up a little bit?
I think so.
Another way of looking at this and probably the easier way to do this problem, to be honest. What's another way of doing this problem? Any ideas? Is there anything we could do that would not do the product rule? Yeah, we just multiply shit out, right? We start out with 2x squared plus 5. We have x cubed minus 7x. Just multiply it out. I've got 2x to the 5th power minus 14x cubed plus 5x cubed minus 35x. So that's 2x to the 5th power minus 9x cubed minus 35x. And when we do dy dx here, the derivative of 2x to the 5th is simply 10x to the 4th. Here we bring the 3 down, negative 9 times 3 is negative 27. We lower that by a power, and negative 35x, x just goes away. And we get the same thing. And I actually think it's easier here. So with polynomials, that's only because we only have 2 terms. As you'll see later on, when we have more terms, doing this product rule is a lot easier. Like if we had one of these to the 3rd, like one of these parentheses to like the 4th power, we're going to do something called the chain rule. And it's a lot easier just to leave it as is and not multiply everything out. Could you imagine having something like to the 7th power and trying to multiply out a binomial? That's a pain in the butt. And when we had the Pascal's triangle, we could do it, but it's still a lot of work. So this product rule speeds stuff up. Let's do another one. Any other questions before I go, though? So we're gonna find f prime of t. Given f of t equals 1 minus t squared times the square root of t. Why don't you guys try doing this with the product rule? Recalling that square root of t, another way of writing it is t to the 1/2. And the power rule still works here. Just because it's a fraction doesn't mean we can't bring the power down and lower it by 1. So give this a try for a couple minutes and then we'll do it together. All right, let's give this goose a gander. Let's give it a try. So like if this is A and this is B, I need to do A prime B plus AB prime. So 1 minus t squared derivative times t to the 1/2 plus 1 minus t squared times t to the 1/2 with the derivative on that one. So the t to the 1/2 here doesn't change. This one minus t squared doesn't change. The derivatives would be in red. The derivative of this is negative 2t. And the derivative of this is 1/2 t to the negative 1/2. So we distribute that out. This is negative 2t to the 3/2. And this is 1/2 t to the negative 1/2 minus 1/2 t to the 3/2. And it looks like we can combine like terms. And I've got negative 2 minus 1/2 would be negative 5/2 t to the 3/2 plus 1/2 t to the negative 1/2. If you wanted to write this back in terms of roots, we have negative 5/2 t square root of t plus 1/2 root t. Yeah, there's an easy way of doing this. Just like we said with the last one, just multiply it out. I've got t to the 1/2 minus t to the 3/2 or 5/2. And so if I do the derivative there, I just bring the power down and lower it by a power. 5/2 minus 1 is 3/2. But as I was saying, there's cases where this product rule is essential. Polynomials, I don't know that it is. Like small polynomials like this, not really. We're gonna be doing trigonometry functions and stuff here in a little bit too. So if you've got x times cosine x, you really kind of have to do this product rule. You don't have a way of multiplying it out yet. One day you will learn the polynomial expansion for cosine and sine. Wow. We can write cosine and sine as terms of polynomials. That's some next level shit. I don't think we do it in Calc 1. I think that's a Calc 2 topic, but it's definitely before Calc 3. Yeah,
Where'd you get the negative 5 from? The negative 5 over 2.
I combine here.
Yeah.
I added negative 2 and negative 1/2. So -2 and -1/2. If I get a common denominator, this is 2 times 2. Minus 1/2. So -4/2 minus 1/2. All right, so they'll give you shit like this. Suppose u and v are functions of x that are differentiable at x equals 0. And they give us values of each of those things. U of 0 equals 5. U prime of 0 equals -3. V of 0 equals -1. And V prime of 0 equals 2. Find the value of the derivative of the product of u and v at x equals 0. So we don't even know what the functions u of x and v of x are. Don't know. Awesome, don't know. We do know how to do the derivative of u and v though. We take the derivative of the first term times the second, plus leave the first term alone and take the derivative of the second. And since we're evaluating these at 0, this becomes like this. Because this was shorthand notation for u prime of x, v of x, plus u of x, v prime of x. Well, they give us values for these. U prime of 0 was listed as -3. V of 0 is listed as -1. U of 0 was given as 5. And V prime of 0 was given as 2. So this equals 3 plus 10 is 13. That's the product rule. We've looked at the addition of derivatives, this difference, the sum of derivatives, difference of derivatives, the product of derivatives. What arithmetic thing are we missing? Quotient, division. The quotient rule is so we do require v of x doesn't equal 0. Because otherwise we can't have it in the denominator. So we're looking at u of x over v of x. And then we want to take the derivative of that. It looks similar to the product rule on top, but it's not. There's a minus sign. If you remember it like this, you are a champion of fucking mathematics. The way many of us remember it is if we have high on top and low on bottom, it's low D high times the derivative of the high, low D high minus high D low, all divided by low squared. LDH minus HDL over L squared. You're gonna hate this. Guess what? I still hate the quotient rule. I still do. I fucking hate it. It's tedious. When we get to 2.6, we're gonna do something called the chain rule. And I'll show you how to rewrite this as a product rule instead. I think the product rule is easier to remember. This is just like tedious. Let's walk through an example though. So I have y equals t squared minus 1 on top, t cubed plus 1 on bottom. And I want to do low times the derivative of the high minus the high times the derivative of the low, all over low squared. So this is my low and this is my high. Yeah.
So you know how the G and the G of X and F split? That's the first one,
Uh-huh.
compared to the product rule, can you leave it the same, you should make that minus sign? It's not confusing, like they're the same, you just minus,
That's one way of remembering it.
yeah.
Yeah, because you'll see, I mean, like if I change the order of this,
So same thing.
this looks like U prime V minus UV prime. So like the product rule is U prime V plus UV prime. So it looks like the product rule, but it's a different sign. Which is probably the easier way to remember it, to be honest. Fuck all this low D high, high D low. This is the way I learned it. Let's just do the product rule on top, but use minus sign. Fair enough? We just got to remember which one is subtracted. So the one on top is the derivative for the first one. I'll do it both ways. So the low D high method, I'm going to do low, which is t cubed plus 1 times the derivative of the high minus high, which is t squared minus 1 times the derivative of the low, all over t cubed plus 1 squared. The only difference between doing this way and the one that looks like the product rule is that these would be switched. T squared minus 1 prime, t cubed plus 1. Well, let's just figure out what they are. The derivative of t squared minus 1 is just 2t. And this is 3t squared. And we still have t cubed plus 1 on bottom squared. The derivative's technically done. You should probably clean it up, though. Remember to distribute the minus sign to each thing just once, not to both parentheses, just one parentheses. So I got a minus and a minus, will be a plus here. So this will clean up to dy dx equals -3t to the fourth. Oh, wait, I got a plus 2t to the fourth. I can put those two together. That's a -t to the fourth. Plus 3t squared plus 2t. All over t cubed plus 1. I'm going to leave that squared like that on bottom. No need to multiply that out. And since I got that squiggle shit over on the left, I'm going to write the dy dx over here. There's actually only one more problem in this section. I'm going to show it to you guys. And then I'm going to make a video for it later today and I'll post it. So given y equals x squared plus 1 over x minus 1, find all the values of x at which the tangent line is horizontal. Back to Matthew's question. When are we doing the tangent lines with this shit? Be patient with yourself with the quotient rule. Be patient on the product rule. Product rule is a little bit easier than the quotient rule. The quotient rule is all about, you just got to memorize the formula. The product rule is a little bit easier where you can just go, I'm just going to rewrite them all a bunch of times and then I'm just going to take the derivative of them one at a time. Where this video will be posted is where I've been posting other videos. I'll put it back up in a second. Like the other day, we had stuff in 1.8b. I did an example video here. I posted it here along with what I wrote. It's like a 6-minute video or some shit like that. When we did 2.2, we had a couple examples that we didn't do. That we just wrote the lecture for, but I made a short video on those. This is like 8 minutes or some shit like that. So come in and take a look at them to see like a little bit more, finish out what we've done. And this is where I will post today's video and this little extra video. In fact, right before this class, Jose asked me to show him an example on the continuity. One of the homework problems on continuity. Yeah, I think it was problem number 5. Like it's a little confusing. I think Cynthia asked me about it at the Mesa Center. It was one with the f of x was a piecewise function and g of x was a piecewise function. And it says where are these continuous and does like the product and does absolute value. And so I walked through another example. I did this before class. That'll be another video that's posted. Other than that, I will see you, ladies and gentlemen, on Thursday. Peace. GTFO. You too, Voldemorta. Have a good day, everyone online. Yeah, that's your name.